Okay, so what happens if we put more than one capacitor in a circuit? How does the circuit respond to the fact that there's more than one capacitor there? So we're just going to do the two sort of simplest situations, which is where we put capacitors in series with one another, and then when we put capacitors in what we call parallel with each other. So this is a basic series circuit where I have a voltage source, a DC power supply over here, which I'll mark it as a V. Actually, that might be the best way to do it, but we'll mark it as a V source right now. It's not typically the variable I'm going to use for these things, but before we introduce that, we'll call it that. And so then what we have is we have three capacitors, capacitor 1, 2, and 3, and they're all in series in the sense that if there was going to be current that flowed here, it would have to go through all three of these. There's no way to get to, say, capacitor 2 without going through capacitor 1. And you can't get to capacitor 3, they're all connected in series to each other. This is what series looks like. And then I've got over the side the fact that capacitor 1 should be the amount of charge which builds up on capacitor 1 over the voltage drop across capacitor 1. And again, the voltage drop I would measure by taking a voltmeter, and I'd say red probe here, black probe here, and I'd be able to measure this V1 from that. And then similarly for V2 and V3. And then I can rewrite all of these things like this. I can say, well, Q1 should be capacitance 1 times V1, or V1 can be written as Q1 over C1, V2 is Q2 over C2, and V3 is Q3 over C3. And again, each of these are building up that charge on either side. Now, all the Q's basically have to be equal, the amount of charge that builds up. So what's going to actually happen here, right, is you attach a wire from this side of Q of capacitor 1, and the other side goes and touches the positive terminal of the voltage source. Well, that's going to allow a positive charge to build up here. And then on the opposite terminal, you're going to get the exact negative opposite of that. Well, now I have another wire. I have a wire here, which goes basically from this side to this side. And so the amount of charge which is going to build up here, right, this is a conductor, the amount of charge that builds up there, Q2, has to be plus Q1. Because it's happening in response to the fact that there's a negative Q1 on this side. And so all the charges, so then this ends up being a negative Q1, this again becomes a positive Q1, and then this becomes a negative Q1. So the charges are all equal to each other. Q1 is equal to Q2 is equal to Q3. We just call that Q in this case. And that means, again, that the Q's come from this. Now the total voltage drop across all three capacitors has to add up to this source voltage. The amount of, if I went and I measured, again, a voltage drop, if I said this is the high side, and then I took with my probe, if I have my probe and I go, here's my voltmeter, and I have the red there, and I have the black here, which is on the other side, this is going to also be the same as if I stuck the red probe here and I had the black probe here. This is just wire in between, right? This is just wire. From here to here is just wire. And so if I have the red probe here or the red probe here, it doesn't make any difference. Similarly, there's just wire between here and here. And so I'd get the same measurement. V1 plus V2 plus V3 have to add up to that V source. If I plug in that V1 is Q1 over C1, Q2, and all this, I can basically say, well, those Q's are all the same. So it comes out, and I just end up with this weird 1 over C1 plus 1 over C2 plus 1 over C3. We can write that as the equivalent capacitance, where 1 over the equivalent capacitance is just this inverse sum of all the other capacitors. So you have capacitors in series, they can act as basically one equivalent capacitor, where that equivalent capacitor can be found by using this, what we call an inverse sum. This is where it would be really good to familiarize yourself with the x to the minus 1 button on your calculator. And I'll do a problem with this in a second. We'll see how that can really help. But that button is extremely helpful in doing additions like this. We'll do something very similar when we get to resistors in circuits as well. Now we can also have capacitors in what we call a parallel circuit. So this is parallel capacitors. And you can see the difference between this type of wiring and, again, this one up here. So here it's basically just sort of one loop, sort of one room, and all the capacitors are connected to each other in this series way. Whereas here's my voltage source, and each of the capacitors is able to independently get back to this voltage source without having to go through another capacitor, right? It can get all the way to the positive terminal, and they can get all the way to the negative terminal without having to go through another capacitor. And that's what we call parallel wiring, where they're in parallel to each other instead of being in series to each other. Again, we can write the capacitance in terms of the amount of charge that builds up. Here, the amount of charge that builds up is not the same. It's not the same, but the Vs is the same. So they all have the same voltage drop. And so C1 is Q1 over V, but more importantly, we can say that the amount of charge that builds up Q1 has to be the capacitance 1 times that voltage drop of our source. So this is our voltage source. The Q total that builds up, the total amount of charge that builds up, is Q1 plus Q2 plus Q3. And that turns out just to be the sum of the capacitance all times the voltage source. So again, we have an equivalent capacitance, which is the sum of all the capacitances of the ones that are connected in parallel with each other. So let's look at an example here. Number 11, it doesn't show the voltage source here. It just says there's a voltage difference across these two different places. But I'll go ahead and I'll draw it in as, so basically they're saying that there's some source that's producing something here, which we're calling V. And it wants us to find the electric potential. The equivalent capacitance. So C equivalent for this. All right, so this is actually a combination of a series connections and parallel connections. It doesn't seem real obvious here possibly, but C1 and C2 are parallel to each other. I could redraw C2 instead of having it there. I could draw it here, right? It doesn't make any difference whether it's on this branch or that branch. This is all just a wire. This is a wire from this place, and this is another wire to that place. And so C1 and C2 are in parallel with each other. And so C12, this is the equivalent resistance of, the equivalent capacitance of capacitor 1 and capacitor 2 is just their sum, right? Because that's what we do if things are in parallel. And so they're going to say 10 microfarads plus 5 microfarads So 15 microfarads. That's C12. And so then I could now redraw this and say, okay, now I have another circuit where instead of C1 and C2 being separate ones, I can say I have a capacitor C12, and then that is connected in series with capacitor 3. And so C12 and C3 are in series with each other. So I could say there's an equivalent capacitance C123, which is the sum of C12, or the inverse sum of these two added together. Let me make another sheet. So C123 is 1 over 15 microfarads plus 1 over 4 microfarads. Now, this is what I'm going to do on my calculator. I'm going to type 15, 1, 5, and then I'm going to do the x, the minus 1 button. And I cannot switch things over into microfarads because they're both in microfarads. So what I'm going to get out is going to be in microfarads. So I'm going to say 15 x to the minus 1. And I'm going to say 4. And then I'm also going to do x to the minus 1. So I say plus 4 x to the minus 1. Then I'm going to say the equal button. And then I'm going to do x to the minus 1 again, and equal button. And I get out there, I get a number which says 3.159, so we'll just say 3.16 microfarads. This is my answer. You can do it the long way, but that's the best way to go. It's much, much faster to do this on your calculator, because what you get back out again, remember, is 1 over the answer that you want. So if you did 15, if you said, oh goodness, 1 divided by 15 plus 1 divided by 4, I get 0.316666, but remember that I want the inverse of that, so I need 1 over that again, and that's where I get the 3.1. I'm actually going to write this out so it's clear that we're talking about. So this is 3.158 microfarads. When you're adding things in parallel, using that x to the minus 1, or sorry, when you're adding things which need that inverse sum, using the x minus 1 button makes things a lot simpler. So this is actually, when I say equal sign, I really mean the enter sign on my calculator. Okay. Another thing we should discuss before we move on to chapter 26, so I'm going to do that in a separate video, is that because capacitors are storing up charge, they hold all this charge in them, that means they also store energy. And so the stored potential energy in a capacitor we write as U, capital U for energy, stored potential energy, and it's essentially it's Q squared, the amount of charge squared over 2 times the capacitance, or if you want to stick in the relationship between capacitance and C and V, it can also just be 1/2 the capacitance times the potential difference squared. So in number 31, they tell us that we have a capacitor, which is 2 microfarads, and then we also that's capacitor 1, and then we have a capacitor 2, which is 4 microfarads, and it tells us they're in parallel. So that means that the equivalent is just the sum. So we have 6 microfarads, and then we want to know the total energy stored in the capacitors if they're connected by, or they are connected to 300 volts of potential difference. And so our stored capacitance is stored energy is 6 times 10 to the negative 6 farads times 300 volts squared. So 0.5 times 6 to the negative 6 times 300 squared is 0.270, and this is a unit of energy, which is joules. So there's not that much that we're doing strictly in chapter 25 with capacitors. We'll come back with capacitors once we have resistors and inductors. We'll do more with them. All right, I'm going to do the next step in the next video.